In cinematic visual effects, studios render complex computer-generated imagery over weeks or months. In live sports broadcasting, there is no luxury of time. To keep pace with a live broadcast frame rate, the graphics engines powering athletics must ingest millions of telemetry data points, calculate intricate three-dimensional geometries, and composite photorealistic graphics in less than 30 milliseconds. Creating these seamless overlays requires an immense technological infrastructure. Behind every floating statistic or perfectly anchored advertisement is a network of radio frequencies, complex volumetric meshes, and artificial intelligence models. Blending physical and digital worlds live on screen represents some of the most advanced spatial computing on the planet, executing complex renderings faster than the human eye can blink. The yellow first down line in American football is the gold standard for invisible visual effects. Drawing a straight, two-dimensional line across a video feed is simple, but projecting that graphic onto an imperfect physical surface is a major mathematical challenge. This animated diagram illustrates the topography of a professional football field. It is not perfectly flat, featuring a slight convex crown in the center to facilitate drainage. Technicians take laser measurements to create this precise three-dimensional mathematical mesh of the stadium. The system mathematically draws the virtual graphic directly onto this invisible mesh. The line bends to match the physical turf exactly, preserving the correct pitch and perspective. To keep that line anchored while the camera moves, broadcasters use instrumented cameras. Optical encoders mounted on the pan, tilt, and zoom mechanisms transmit precise positional and focal data over 30 times per second, allowing the rendering engine to calculate the exact pixel coordinates required to lock the graphic to the physical turf. Making the line appear beneath players requires advanced color filtering. The system uses a specific color palette of greens and browns representing the field. If a player's uniform or a white cleat intersects the mathematical line, the system recognizes a color mismatch and suppresses the yellow pixels, creating occlusion. Because this functions like an inverted green screen outdoors, technicians must constantly recalibrate that authorized turf color palette throughout the game to account for passing clouds, creeping stadium shadows, and deteriorating field conditions. What appears to the viewer as a simple painted line is a highly dynamic mathematical intersection between a three-dimensional field mesh and live optical telemetry. While a static field mesh anchors basic graphics, deep analytics require tracking the exact coordinates of moving athletes and objects in real time. Broadcasters and leagues build massive spatial tracking architectures to gather this data. This tracking methodology matrix compares the three primary technical approaches used across different sports tiers: wearable radio frequency identification, optical skeletal arrays, and machine learning video analysis. Wearable sensor hardware outputs precise X and Y coordinates, speed and acceleration data at a frequency of 10 to 25 Hz. Hertz is a unit of frequency measuring the number of cycles or data transmissions per second. The National Football League implements this through an active ultra-wideband network. 20 receivers mounted strategically around the stadium infrastructure continuously ping active tracking chips embedded directly between the layers of every player's shoulder pads. Optical array tracking relies entirely on high-resolution camera networks rather than physical hardware worn by athletes. Permanent stadium installations utilize dedicated 8K resolution cameras to create a stereoscopic digital twin of the field. Modern optical systems have evolved from simple center-of-mass tracking, which identifies a player as a single moving dot. Today, advanced machine learning maps up to 29 individual skeletal points on an athlete's body, analyzing precise biomechanics like knee bend angles and arm slots. This external skeletal data is fused with internal hardware telemetry. FIFA World Cup systems utilize an inertial measurement unit suspended inside the match ball. An inertial measurement unit is an electronic device that measures and reports a body's specific force and angular rate. This internal sensor continuously transmits impact data at 500 Hz to pinpoint the exact millisecond of a kick. Artificial intelligence merges that 29-point skeletal mesh with the high-frequency ball impact data to instantly render three-dimensional virtual offside lines, reducing video review times from minutes to seconds. The third methodology is purely software-based. Sensorless artificial intelligence estimates the camera pose by calculating vanishing points through visual inference alone. This relies on GPU-direct, remote direct memory access. GPU Direct RDMA is a hardware technology that allows massive streams of raw video data to bypass the computer's central processor and stream directly into the graphics card for immediate compositing. Broadcast tracking has rapidly accelerated from plotting simple bounding boxes into rendering full, highly accurate biomechanical digital twins live during the action. Capturing precise spatial data is only the first step. Translating millions of raw coordinates and sensor readouts into readable, dynamic on-screen graphics requires a highly specialized data engineering architecture. Modern Formula One racing serves as the gold standard for real-time data integration, operating vehicles that function as high-density physical sensor platforms. Every vehicle on the track is outfitted with over 300 physical sensors. Together, they generate 1.1 million distinct telemetry data points per second, encompassing minute fluctuations in tire pressure, engine component temperatures, and lateral G-forces. This flow architecture chart maps the cloud infrastructure required to prevent bottlenecks. The colossal data stream is formatted as line-delimited JSON, a lightweight data interchange format ensuring continuous streaming. The data is ingested using Apache Kafka, a platform built for high-performance data pipelines. Data processing engines like Spark Databricks process the raw numbers into calculable metrics, such as average sector times or predicted pit intervals, pushing them directly to the rendering engine to dynamically update on-screen overlays with mere milliseconds of latency. Real-time visual storytelling in sports is effectively a massive, highly synchronized cloud-based data brokering operation functioning entirely behind the scenes. This deep spatial awareness and low-latency data pipelining directly enables sophisticated, real-time broadcast monetization. Digital billboard replacement technology allows broadcasters to target the physical perimeter LED boards located inside a stadium and replace them with digitally rendered virtual overlays intended solely for the television audience, enabling multi-region market segmentation from a single broadcast feed. Artificial intelligence mathematically interprets the depth and physical geometry of the stadium architecture. It seamlessly masks out the physical advertising boards and replaces them with localized virtual advertisements, constantly accounting for complex visual variables like fast players running in the foreground or dynamic shifts in stadium lighting. The extreme volatility of live sports viewership presents a major computational challenge. When a championship game enters overtime, the audience can surge by millions in minutes. If ad servers fail to auction and load inventory fast enough during these surges, it results in auction timeouts and massive revenue loss. To solve this bottleneck, ad tech platforms pair high-performance graphics processing units with inference servers to accelerate the AI auction decision-making process. An inference server is specialized software designed to execute trained machine learning models to make rapid predictions or decisions. This comparative bar chart shows the results of that hardware acceleration. The inference latency drops from an industry-standard 5 to 10 milliseconds down to roughly 1 millisecond. This results in an 85% reduction in auction timeouts. This extreme speed allows brands to deploy autonomous AI agents to target highly specific game moments. If an advertiser wants to display their logo immediately following a dramatic three-point shot, the AI continuously analyzes telemetry and executes the buy in microseconds. Live spatial computing instantly and continuously monetizes the audience's attention at a sub-millisecond scale. The absolute frontier of broadcast technology is moving rapidly beyond planar two-dimensional video feeds, entirely in favor of real-time, three-dimensional volumetric capture. Deep learning algorithms ingest dozens of high-resolution cameras simultaneously, instantly generating a continuous three-dimensional spatial mesh of a live action as a dense point cloud. This immense processing power allows broadcast directors to execute impossible virtual camera angles entirely synthetically, freely flying the viewer's perspective under the basket or from the point of view of the ball itself within seconds of the play occurring. Transmitting this level of immersion to end users creates a massive bandwidth challenge, particularly when streaming 180-degree stereoscopic video to advanced virtual reality headsets like the Apple Vision Pro. This schematic demonstrates the MVHEVC encoding standard. MVHEVC is a highly advanced video compression format designed specifically for multi-view and stereoscopic 3D content. By utilizing temporal and spatial references, it reuses data blocks from the left eye's image to render the right eye's frame. This technique drops the overall required bitrate by 33%, streaming a massive 4K per eye stereoscopic feed at an efficient 36 megabits per second. Current rendering pipelines reconstruct physical games into fully explorable digital spaces on the fly. Historically, executing high-quality sports visual effects required multi-million-dollar outside broadcast fans and arrays of proprietary mainframe servers. Today, sheer computational power and software optimization had completely democratized these tools. Standard local PC graphics units can now parse live XML data. Extensible markup language is a simple text format used to store and transport structured data. These PCs then composite dynamic visuals over standard NDI networks. NDI, or Network Device Interface, is a protocol that allows high-quality video to be transmitted over a local area network in real time. This makes network-quality, data-driven broadcasting highly accessible to high schools and independent streamers. But regardless of whether a broadcast utilizes 29-point skeletal meshes or programmatic microauctions, the technology must serve the authentic human drama. Early experiments, like the heavily criticized glowing hockey pucks of the 1990s, failed because they drew excessive attention to themselves. The ultimate goal of modern spatial computing is to illuminate the underlying athletic achievement and then fade entirely into the background. The absolute pinnacle of live sports engineering is successfully executing billions of complex spatial and commercial calculations per second and ensuring the viewer never notices a single one.